All right. Thank you all so much. First of all, I just want to give a big thanks to Code Blue for having me out here. It's been a pleasure to visit Japan. I've been having a great time so far, and thanks to all of you for coming to this talk. I'm really excited to talk to you all today about some research that I performed, performing fuzzing on Mach messages, a form of inter-process communication on Mac OS and iOS. So without further ado, let's get into it. A quick little bit about myself. I am a senior security engineer on the information security engineering team at Google, ISE. I perform product security reviews on Google products, as well as perform 20% research with Google Project Zero, looking for 0 days and trying to exploit them on a variety of systems, but typically focus on the Apple ecosystem. Before that, I worked with Mandiant on their red team. I was doing mostly application security pen testing, source code reviews, and embedded device assessments. And then I also spent some time on the Flare team, which is Mandiant's reverse engineering team, doing malware analysis and looking for O-days being exploited in the wild. So today, I want to start by giving you a bit of a crash course on fuzzing as a concept for vulnerability research, as well as a little bit of a background on what Mach IPC is and how interprocess communications work in the Apple ecosystem. Then I'm going to walk you through the specific attack cycle that I took to both find and exploit vulnerabilities and the specific fuzzer that I wrote to do that. And then finally, we'll leave some time for a couple of takeaways and hopefully some questions that you all have. So I hope this is going to be an inspiration for those who are interested in the space, and as well as useful technical content for those well-versed in Mac OS research already. So let's start at the very basics of fuzzing. What is it really? And the definition I like to use is sending unexpected inputs to a system in the hopes of simply making something unexpected happen. And that can be a crash, that can be some sort of log being triggered. It really depends on what you're trying to do. Most of the time when we're looking at C and C++, we care about a crash because it might be exploitable via memory corruption. But the approach that I like to use when fuzzing, and especially on Apple systems where most of the code is closed source, is this idea of knowledge-driven fuzzing. So this balances automation, which is fuzzing. This is used to quickly identify interesting inputs, and you might not fully understand the code base when you're doing this. You're just throwing things at it and seeing how it reacts. Kind of this idea of moving fast and breaking things. But you don't stop there. You couple that with manual analysis. So you look at the code coverage, you look at what parts of the code the fuzzer's exploring, and you say, why is the code coverage getting stuck or plateauing? You might say, why is the fuzzer causing these strange errors? How can I move past these and help guide the fuzzer past these errors? And through that, you develop an understanding of the code base. So this is a really valuable approach to vulnerability analysis I've found because it couples that automation with being able to really understand the code base well. So the attack cycle that I used for this research was to identify an interesting attack vector, then choose a target that used that attack vector. In this case, it's going to be Mach messages. Create a fuzzing harness, start fuzzing and produce crashes, and then look at those crashes, see if they're interesting, look at the code coverage, and probably then we need to iterate on the fuzzing harness to improve it and to get deeper into the code base. We complete steps 4 through 6 a bunch of times until hopefully we eventually identify a security relevant crash and can then turn that into an exploit of a vulnerability. So the first step, identifying an attack vector. So you might know in the modern web browser landscape, exploiting a browser such as Chrome or Firefox typically requires an additional sandbox escape vector these days. It's not enough to just get an RCE in Chrome. And one well-used escape vector for these within browsers is inter-process communications, because they serve as this natural bridge between restricted and unrestricted processes. So you can see here, Mach is serving as that bridge from the web browser process, which is sandboxed, to the unrestricted message handler. Mach messages do have quite the history of abuse. I linked to a couple of recommended readings here. A couple from Ian Beer of Project Zero did some really nice work showing how Mach messages can be used for heap spraying, as well as sandbox escapes and privilege escalation. Another great blog post I recommend if you're interested in learning about Mach messages and fuzzing is this one from Ret2 Systems here, a methodical approach to browser exploitation. They go through finding a Safari exploit and then using fuzzing to chain that with a sandbox escape at pwn to own. Perfect. So let's get a little bit into what these Mach messages are. And to understand a Mach message, we first need to understand a Mach port. A Mach port is basically just an IPC message queue that is handled and managed by the kernel. And there's this notion of a port write. So this is a handle to a port that either allows sending to it if it's a send write, or receiving to it if it's a receive write. To give you a little bit of a practical example of how you would establish a Mach IPC connection, and how this is often done on modern macOS, is via the Bootstrap server. So this is a special Mach port on the system that helps establish connections with other Mach ports. And by default, any process on the system has a send write to the Bootstrap server. Then we have this notion of a Mach service, which is a Mach port with a name that is registered with that Bootstrap server that everyone can talk to. So, for example, if we want to register a service called com.apple.codeblue, let's say we have two parties here, Alice and Bob. Alice would allocate a new Mach port with a receive write. Then she's going to register her service using that specific application identifier, com.apple.codeblue. And by doing that, she's giving the Bootstrap server a send write to the port that she has a receive write to. Then Bob comes along and asks the Bootstrap server for the service by the name com.apple.codeblue, and the server gives Bob a copy of the send write to Alice's Mach port. And now Bob can send messages, and then Alice, with her receive write, can fetch them. So we've established a communication channel here. So now that we know a little bit about the basics of Mach IPC, it was time to choose a target that utilized Mach IPC. And to do that, I started looking at the system daemons available on macOS. System daemons are special services that run on the system, and they're spawned by launchd, which is the kind of first process that runs when the OS is booting up. These are all defined in plist files in the launch agents or launch daemons directory. So you can see an example here. We have the address book assistant service. This is going to be a Mach service that runs on the system, and you can connect to and send messages to that service. So cool. I knew I wanted to look at Mach messages. I knew I wanted to find these interesting system daemons running on the system, many which run with high privileges. And so it kind of led to this bit of a Venn diagram situation where I wanted to narrow down from kind of all macOS processes as potential targets, then look at ones that just exposed a Mach service, and then finally hone in on ones with a Mach service that you could talk to from a sandbox. So when we think about those browsers, once again, we'd like to break out of them. And to do that, we need to find a Mach service that is actually accessible from a sandbox process like Chrome. So to do that, we can actually look at these things called SB files on macOS. These are written in tiny scheme format, and they basically specify all of the different Mach service names that a given process is allowed to communicate with. So here we have an example for the Safari WebKit GPU process. And as you can see here, it's identifying, or it's specifying a few different Mach services that it can send messages to. So immediately these start to look like pretty interesting attack vectors to target. Another way you can do this is dynamically, and sorry, I'm just gonna stop this from popping up. Perfect. Another way you can do this is dynamically using the SB tool, which is written by Jonathan Levin, a really great macOS researcher. It uses the sandbox check API to determine which Mach services a process can send to dynamically. So here we can run the SB tool looking for Mach services and enumerate a bunch of them. I believe this was running on the Safari process. So we have these messages handlers we can send to, and then these immediately become a potential for sandbox escapes. So with that, the target that I chose to really hone in on even more is the CoreAudio D service, or binary. This is a launch daemon on the system. It exposes this complex service called COM Apple Audio Audio HALD, and it allows Mach communications from several impactful applications, including the Safari GPU process that we just saw. It also had a large number of message handlers that we could interact with and invoke, as we'll see. And the service seemed to control audio hardware on the system, and so it would likely require elevated privileges to do so. Also, the CoreAudio D binary and the CoreAudio framework that it used heavily are both closed source, so it would be a unique reverse engineering challenge. So the next step, now that we had our target in CoreAudio, was to create a fuzzing harness to fuzz these Mach IPC message handlers. What is a fuzzing harness, you ask? It's literally just code that allows you to send input through an attack vector. Basically, call a desired function. And when we're talking about fuzzing harnesses, this even comes up because the entry point really matters when you're talking about fuzzing. Fuzzers can find a whole lot more than just surface level bugs. It's a lot more impactful than just pointing it at a command line argument and letting it run. But we have to actually point the fuzzer towards the correct area of the code that we want to target. We have these things called coverage-guided fuzzers that retrieve feedback from the fuzzer as it runs and look at where the fuzzer is actually exploring in the code. And they can see when if conditions are actually being properly passed. But this is only going to be powerful if the energy is focused in the right place. And so the right place to fuzz is very deterministic. It depends a lot on the ease of development. You might want to do something really quick and maybe forego targeting deep parts of the code base. Or you might want to keep your environment more realistic. You might care more about increased performance versus having more false positives to triage through. And so it's very highly dependent on the target and research goals. But I will walk you through the process that I took to figure out where to target and write my fuzzing harness to attach to. So when fuzzing these Mach message handlers, the first option that I really had was to call the Mach message API naturally. So the Mach message API is the way that you would normally send a message to a process on the system. And so it would be pretty easy to just write code that we could have the fuzzer send inputs to that would just call Mach message. That would then be sent via the Mach IPC to the kernel managed message queue, and then that would be delivered to the Mach message handler. So the pros of this, it's very simple, and it's very similar to how we will actually exploit the bug if we find one, but it's very slow. We have to wait for the application to send messages and have the kernel process them. There's also many points of potential failure since we're involving the kernel here in two different processes. And probably most importantly, we're dealing with two different process spaces here. And so that makes getting code coverage or getting information about the target and where we are actually reaching very difficult. It also becomes difficult to determine which message actually caused the crash because you have so many different ones that the kernel is processing. So the other option would be a direct harness. So instead of using the Mach message API, we could load code implementing Mach message handlers and then call the handlers directly with desired input. So this way, it's very fast. We're in a single process, so it's easy to instrument and get code coverage and determine how we're doing. And then it's easy to know which input caused the crash and replicate it. However, it is a bit different from the end exploit, and we might have to invoke initialization routines because we're calling code deep within a library, and there might have been startup or initialization code that we aren't calling as part of our fuzzing harness. So I ended up choosing this approach for the pros that you see here, mostly it being in the same process space. This would be very important for obtaining code coverage from our fuzzer. So the idea here would be first identify the Mach message handling function, so the code that's actually parsing incoming messages, then write a fuzzing harness to load the message handling code from CoreAudio D, and then use a fuzzer to generate inputs and call the fuzzing harness. Then hopefully we would profit and find some interesting crashes. So this first step here, find the Mach message handler, find the code that's processing the incoming messages. I started looking at the CoreAudio D binary for the service name that we knew Chrome and other browsers could talk to, this audio HALD service, but there were no references to it in the binary. However, I did notice that the CoreAudio framework, which is a library, a large library, is loaded by the CoreAudio D process. So that seemed like a good candidate to look at next. However, I went to find the file on disk and got a message, no file or directory. So that's pretty interesting, I thought. There's this concept on macOS, though, of the Dillon shared cache. Starting with Big Sur, most framework binaries are actually not stored on disk. They exist in the Dillon shared cache for performance reasons. However, you can extract them pretty easily. There's a lot of third-party extractors. I'm linking to one here. You can also load the Dillon shared cache bundle directly into IDA Pro or Binary Ninja, probably Ghidra as well. I haven't tried it. And it will parse it out nicely for you and give you the individual libraries so you can continue to reverse engineer. Cool. So now that I was looking at the CoreAudio library, the code that was handling the meat of this logic, I did identify the bootstrap check-in call, which is where the service name is actually registered with the bootstrap server. So then we knew that we were looking at the right code for processing this service. Now we actually had to find the function that processed the incoming messages, though. To do this, we need to know a little bit about MIG subsystems. Many Mach services use the Mach interface generator, or MIG. This is a interface definition language, and it's useful for developers because it abstracts away a lot of the Mach layer, which is very low level and a bit cumbersome, and makes it much easier to write client-server code. It's pretty easy to grep for these symbols. As you can see here, I'm just grepping for subsystem after dumping the symbols from CoreAudio, and you can see there's both a MIG client and a MIG server. So here, we care about the MIG server. So I identified where that subsystem was being referenced, and it's in this block, which you can see in IDA Pro here. We basically have an incoming message in the RDI register, and then that is being, the message ID is being extracted from that. It's fetching a value within the struct, and then it's getting the subsystem offset, doing an index lookup for the MIG subsystem, and then calling a function based on that message ID. So with that, we have the ability to call a bunch of these RPC functions. So these are the message handlers that the MIG subsystem is then routing the incoming message data to. And there was about 63 of them for CoreAudio, I believe. And nicely, they all start with this double underscore X prefix, which makes them easy to identify in IDA Pro. Cool. So we knew where the message handling was happening, but now we needed to figure out how to actually call this code directly. And that actually becomes a little bit difficult because this symbol is not exported. So we can't just simply, we can't just DL open and DL sim because it's not exported. So, but what we can do is borrow some logic from some very nice libraries. The one I chose is tinyinst. It's written by Yvonne Fratrick. We'll talk about this more later. It's very, very useful. But basically, it's able to parse the Mach binary headers and load commands, extract the symbol info, and then we can use it to resolve and call the target function that we care about, even though it's not exported. And I've open sourced my full fuzzing harness. I'm not going to go through all of the code here. There's quite a bit of switch conditions that you can parse through, but the full fuzzing harness can be found on the Project Zero GitHub. But you can see I'm just calling the harness with a given input. We are actually able to create and send specific messages and have them processed by the message handling code. So we could send messages to the message handler, but this isn't really super impactful or useful if we're just sending garbage data, right? So one of the things that I had to do was figure out how to harvest legitimate Mach messages. In fuzzing, this is referred to as generating a corpus of known good inputs. And the idea is you have this corpus of inputs, and then you start to mutate it and see what interesting things happen when you do that. So a coverage-guided fuzzer will do that mutation for you. You just need to find those initial good inputs. So to do this, I created a quick and easy LLDB script that would break on that MIG handler that we had identified and dump the real Mach messages that were being sent on the system to CoreAudio D. The audio MIDI setup tool on macOS was actually really helpful for this because you can create different devices, different audio devices, and mess with settings on them. And so this was really helpful for generating that legitimate traffic and capturing it with my script. So now that we had a fuzzing harness set up and a list of corpus inputs, it was now time to fuzz and start producing crashes. So to do this, I used the excellent Jackalope fuzzer, which is also by my teammate Yvonne Fratrick. It has a high level of customizability. You can write custom mutators, use custom instrumentation frameworks, use custom sample delivery, so a lot of fine-tuning you can use there. As well as one of the biggest sells for me was how seamless it was to use on macOS. And code coverage is provided with Jackalope out of the box by TinyInts, that library that I mentioned previously. This is really nice. It's a lightweight dynamic instrumentation framework, similar to Frida, which you might have used, but a lot more lightweight, which helps a lot with performance. So once I started running the fuzzer with the fuzzing harness I had created, it immediately started producing crashes. And you might think, wow, that was fast, and I did too. But unfortunately, initial crashes when you're talking about building a targeted fuzzing harness are often not security relevant. In fact, in the beginning, they often indicate a fuzzing harness design bug or an invalid assumption and not a security vulnerability. So the next step then becomes, now that we have a workable fuzzing harness, figure out what's going wrong with it, iterate on it, and make it better. So the first iteration I made on my fuzzing harness was performing proper target initialization. So the fuzzer you can see on the left here is basically bypassing a bunch of bootstrapping and initialization tasks that the actual binary would perform normally. So it might initialize global variables, set up hardware, do some other things, but no, we're just beginning by sending garbage message data to the message handler. So this is going to cause some problems. You see what actually happens on the right. So we need to, in our fuzzing harness, do those initialization tasks so that the receiving process is in a state that it expects to be in. In code coverage, information can be very useful in this case. You can see the green blocks here in IDA Pro are blocks that our fuzzer has covered, and the white ones are ones we haven't explored. So we're always going to the left, you see there at that conditional statement. And you can see it's a little small, but it's saying error, there is no system. So those sort of errors will help you realize, oh, I might need to initialize the audio system before I can send this specific message. So once I had performed that initialization of my fuzzing harness, the other thing I had to take a look at was this idea that I refer to as API call chaining. So another bad assumption I made initially was that all message handlers functioned independently of each other, that they were stateless. However, you can see from one of these messages here, I'm trying to set property data, and it's telling me there is no client, so you can't do that. And that's fair, because a lot of APIs that you will deal with are not stateless, they're stateful, and so you need to call one before you can call the other, and it expects that to happen. And this introduces the idea of the need for structured fuzzing. This gets at the sense that most fuzzers will only accept raw bytes and then just send it to a target. But what if we, instead of just sending those bytes along, we consumed them and did something interesting with them? This is largely taken from Ned Williamson's 2019 OffensiveCon talk. I highly recommend checking that out. But basically what we do is, instead of just taking those raw bytes, we parse it to get a bunch of data, and then from that we enter a while loop, which you see here. We're going to continue going through all the bytes until we've consumed all the data, and then each time we will generate a message ID. So we're basically just going to pull out a 4-byte integer from our data, and that's going to be our message ID, and then based on that we will send a specific message. But then we won't end like normally a fuzzing routine would. We'll continue the loop until we've consumed all the data. And this might seem like a very simple idea, and it is, but it's very powerful, because instead of just sending a single Mach message, we can now let the fuzzer, which is really good at exploring which inputs are interesting, we can now let it explore that process space by sending multiple APIs together and chaining them together. So simple idea, but it has really powerful ramifications for increasing your code coverage. The third iteration that I made on my fuzzing harness was mocking out functionality. So the fuzzer would get stuck exploring irrelevant functionality, and it's really annoying when that happens, but you can use a variety of tricks. One is using C function interposing. So for example, my fuzzing harness was trying to call bootstrap check-in, so register the CoreAudio service again, and that had already happened, so that was throwing an error. We can, however, create our own custom version of this function that just returns kern success, and then have that fire instead of the actual check-in function. So this is useful, and then you can just load this library so that it fires instead of the actual bootstrap check-in. Another thing that happened is there were actually silly bugs that were happening that weren't security relevant that messed up the fuzzing efficiency. So this was actually a null dereference that kept happening and that my fuzzer kept triggering. So it would continually crash the process. And so I needed to actually mock out this functionality and prevent it from happening. And to do that, I used the tinyInst hook API. You could also use function interposing like I just mentioned, but this is a really nice API to use when you're dealing with C++, because it allows you to define code that will fire when you enter a function and code when you exit. So it's very easy to then kind of knock out some of those annoying bugs that might happen. And if you want to look at the full custom fuzzer implementation, that is also in the Project Zero GitHub here. Perfect. The last step was then to identify and exploit a vulnerability. So I'll give you a little bit of background on this vulnerability. First, we'll talk about the hardware abstraction layer. This is a layer that our service was interacting with that manages audio devices, plugins, and settings on the operating system. So when you're messing with the volume or you're plugging in a new audio device, it's interacting with the hardware abstraction layer. And this information all gets stored on the heap in a linked list of Hall's object types. So I used tinyInst once again to write a hook to dump all of them in this linked list. And this made it very easy to understand what was going on and start to look at how these objects were arranged on the heap. You can see the output of that script here. So one other interesting thing, when looking up or modifying one of these Halls objects that was stored on the heap, most of the CoreAudio APIs use this function called copy object by object ID, which took in a unsigned integer, and then it was basically used as an index parameter to fetch the corresponding object within the linked list. So given that pretext, I triggered a interesting crash in this function xio context fetch workgroup port. It was very interesting because it was pretty shallow. So you might see here the call stack is not very deep from that initial MIG server, but it's actually occurring on a call function, which is very interesting from an exploitation perspective. Because if we can affect the data that's being dereferenced there, we can potentially hijack control flow. So looking a bit more in IDA about what was going on here, this copy object by object ID function was taking input directly from us, from our message that we sent, or that our fuzzer sent, rather. Then that was being stored in the RAX register, and then that was being dereferenced at offset hex 68 to fetch another object. Then that object, there was a virtual function call happening. And that is where we actually triggered our crash. So to show you a bit more graphically what was going on, this is known as a type confusion vulnerability because the code was expecting a specific type to be present and to have a specific structure. And so it expected this IO control type that you see in blue on the left. It was expecting a pointer at offset hex 68 that would then point to that second object, which contained a vtable, and then it contains some sort of function. We'll call it get port here. But what we actually had happen is we passed a completely different object that it wasn't expecting. So instead of pointing to the vtable it was expecting, it pointed to garbage data, and we actually had a crash occur. From an attacker perspective, if we can control both that first offset 68 and also the data that it points to, we can potentially hijack that control flow and get code execution. So I reported this to Apple on October 9th, 2024. It was fixed on December 11th, 2024. I do want to just mention as well, I only attempted exploitation on this on an Intel Mac, so this would be x86. Apple Silicon and pointer authentication codes, which we've heard a little bit about already this conference, would make things a lot more difficult because on Intel Macs, return addresses and function pointers are not signed. PAC makes this much harder. So my exploitation strategy here, try to find a way to write data to that offset hex 68 that we saw being dereferenced of any Halls object in that linked list. If we could do that, we could start to form this pointer chain that we need for exploitation. There were a few places that we could do this in the code, actually. One right here, there was a UID that was being parsed from the incoming message and then being set to that interesting offset 68. So I thought this would be a great exploitation primitive. However, that ended up being false because if you remember, the CF string type has an uncontrollable header. That's what we were able to set. But we needed offset 0 of the object pointed to by offset 68 to be an object with controlled data, because then we'd need that to point to our vtable. So that wasn't going to work. We need to write a pointer to an object that we controlled, and then that object would in turn point to data we control. A little bit tricky. So I started thinking about maybe ways that I could do this, and a teammate recommended running CoreAudio with guard malloc, which is a nice memory feature on macOS that can help you catch memory issues. You can pass it this pre-scribble option, and it will allocate hex AA bytes in every freshly allocated memory block. So this makes it really easy to tell when objects don't get zeroed properly and can help you identify uninitialized memory being used. And so I ran that, and then I ran my object dumper script, and sure enough, at offset 68 of this engine object that you see here, there was a bunch of A's that were present. And if you look at that, interestingly, the 6 high bytes are using uninitialized memory. So the A's are in those 6 high bytes. The 2 low bytes were actually being cleared out properly. So this was definitely going to make things a little bit more tricky, I thought, but potentially we could get it to reuse data that we might have previously allocated. So the new exploitation strategy here, first find a way to allocate an engine object, then find a way to allocate a bunch of data that we control, try to get a indirect pointer chain to that controlled data, and then try to get the program to reuse our indirect pointers in the unclaimed memory region when allocating this engine object. And the caveat is that the indirect pointer would have its last 2 bytes zeroed out. So I did find a convoluted path to create an engine object, searching through IDA, and you can see how that happens here. However, it was of object size 776 bytes, which actually ended up making this not work. Because on Mac OS, there's this notion of malloc size zones. So the nano and tiny region, so any allocation leading up to 1008 bytes, data actually will always be cleared before allocation. Anything bigger than that, this will not happen. So unfortunately, this meant that my exploit was dead in the water here. Fortunately, there was another way I found to create an engine object with a size of 1152 bytes this time. This would put it in the small malloc region. The problem here was that to instantiate it, you needed to create an audio plugin, and to create a plugin bundle, you had to be root. So that seemed like it wasn't going to work. But I did identify that there were a couple of naturally occurring engine objects that got created when CoreAudio D started up. So I thought, could we use one of those objects to reuse our sprayed data? One other interesting thing here, system daemons on Mac OS, similar to the Kindle talk that we heard, they continually restart. So we can keep trying and crashing the process, and we essentially get unlimited retries here to exploit the service. So to allocate data, I use property lists, which are very commonly used in the macOS exploitation space. Basically, it's a form of binary or XML data that gets deserialized and stored on the heap. You can see an area of this happening in CoreAudio here. So the property list data that I sent to the service would be parsed from my message, it would be stored in memory, and it would also be stored on disk in a plist. And then that plist actually got reloaded each time CoreAudio D restarted. Perfect. And to create that indirect pointer chain that we needed for exploitation, the CF array and CF dictionary types were very important because they allow you to have nested data types within them and create that structure that we needed for our exploit. And in a plist, you can specify a huge number of elements. So it's basically this massive allocation primitive you can leverage. So the updated exploitation strategy would be, and of course, we're assuming once again that we have an RCE in a sandbox process like Safari. We would call this set property data plist API multiple times, pass a plist containing an array of CF string objects. Then we'd trigger the type confusion, the first time just to crash and restart the process so that it would load our plist into memory. And then we would hope that one of those engine objects on the system that was using uninitialized memory got allocated within our old plist. Then we'd trigger the type confusion again on a random engine object on the system and hopefully get the program to make a call into our previously allocated string. And then we continue trying that until hopefully it worked. To give you a quick visual on what this looked like, so we allocate an array of CF strings. Each of those points to a CF string object. And then there's a raw bytes pointer that you see there, and that points to the actual raw data that we have allocated. What we're hoping happens is that one of these allocated engine objects gets allocated over the top of our CF string array that we previously allocated. And then, but you might be wondering, that will probably then point to the beginning of that CF string, which, as we talked about before, we can't control. Thankfully, though, since those last 2 bytes were getting initialized properly, this would every once in a while cause the stars to align such that offset 68 would point to the raw bytes pointer instead of the beginning of the CF string. So initially, something that seemed like it would hinder us ended up helping us on occasion and making this exploit possible through this way. And as you can see from my object dumper script, eventually everything did line up. We have an engine object here, and then I'm dumping the offset 68, which is going to another pointer, and then that pointer points to the raw data that we then control. At this point, it was just as simple as building a ROP chain, starting with a stack pivot gadget, and then performing a file open on a file in a directory we normally couldn't control, but the CoreAudio D user could. And then encoding things in UTF-16 instead of UTF-8. All right, so let's see a brief demo of this, which I will talk you through here. So just to show you first, we are running as just my normal user on the system, Dillon Franke. If we look, this is a directory that the CoreAudio user only can write to. This library preference is audio. And then we're going to try to create a file in there as the normal user, and you'll see that we can't do that. Permission gets denied. Now we're going to run the exploit. So the heap spraying has already occurred here. What we're trying to do is identify or pick random engine objects and trigger the type confusion. And this is going to take a couple of tries here to do successfully. But we're going to wait for it to respawn and then try again. And we'll keep pulling for the file being created in that directory. And eventually, that will get properly wrote to the directory here. And if we look, it was written by the CoreAudio user. Perfect. Thank you. All right. One quick bonus CV here that this fuzzing harness also found was CB25 31235. This was a double free in CoreAudio. I published a write-up on this. This was patched in May, and I'll be talking about this more later as well. So you can read, I know this was a lot of information coming at you fast. It's hard to talk about all this in such a short talk, but you can read more in detail on the Project Zero blog. I'm also working on a second blog post, which is going to be coming out probably next week about the exploitation piece. And I've also open sourced the fuzzing harness, the custom instrumentation, and the POC crash for the CV that I showed you today. Cool. So thank you all so much for joining today. I hope today that I've showed the power and importance of sandbox escape vectors, talked about knowledge-driven fuzzing as an approach to vulnerability research, and showed the exploitation process of a type confusion vulnerability in CoreAudio D. But most importantly, I hope I've inspired you to do security research of your own. A huge thanks to Ned Williamson, my mentor Yvonne Frotrick, and my wife Isabel. Thank you all so much, and I look forward to talking to you later in the conference.